the driver of a 1 times 10 to the power 3 kg car traveling on an interstate of 35 meters per second slammed on his brake to avoid hitting a second vehicle in front of him, which had come to a rest because of the congestion ahead. After the brakes are applied, a constant kinetic friction force of magnitude 8 times 10 to the power 3 Newton acts on the car. Ignore air resistance. At what minimum distance should the brake be applied to avoid a collision with the other vehicle? B. If the distance between the vehicles is initially only 30 meters, at what speed would the collision occur?
Okay, so there are two cases. Uh, okay, before that, a car is traveling behind another truck. Okay, this is the car is traveling behind the truck, and when the truck in front stop, okay, stop, then the car behind need to stop. Okay, now the distance between the car and the truck need to be a certain minimum distance, right? If the distance is too short, then the car will hit against the truck. If the distance is a bit longer, then the car will not hit the truck. Okay, so in the case if the car will not hit the truck, the final velocity must be zero, right? The final velocity must be zero. So again, we use the change in kinetic energy is the work done against frictional force. So the change in kinetic energy is half mv square. The final kinetic energy is zero. So it's half mv square minus zero. Now this is equals to the work done against friction, the frictional force times the distance. Okay, substituting the velocity to be 35 meter per second, and the distance between them, sorry, the distance between them we don't know, but the frictional force we know is a constant force of 8,000 newtons. So by converting all the kinetic energy into the work done, we can find out what is the distance traveled, right? So we use it again. Kinetic energy is equated with the work done on friction. Okay, so this is the kinetic energy, this is the work done. So we form an equation and solve for the value of D. So the value of D is 76.6 meters. 76.6 meters. Okay. Any questions so far?
No question, sir.
No question. Now, in the second case, the distance between them is too short. It's only 30 meters. Is it 30 meters? Yes. In the second case, the distance between them is only 30 meters. And we have calculated they need at least 76.6 meters to avoid the accident, to avoid the car from hitting the truck. They have to be 76.6 meters apart. But in the second case, they tell us, oh, it's too late already. The distance between them is only 30 meters now. Okay, never mind. Even though it's 30 meters, they just slam on the brake. Okay, so when the driver step on the brake, you will definitely hit the car because the distance is only 30. But what we want to know is just before hitting the car, how much is the velocity? How much is the velocity of the car before it hits the truck? Okay, so that means the initial velocity V naught is actually, we know, is 35 meters, 35 meters per second. But the velocity before it hits the truck, we don't know. So we call it half mv squared. So v square is actually the final velocity of the car before it hits the truck. Now this change in kinetic energy is the amount of energy used to overcome the friction, is the work done on the friction. Okay, so we use this equation to solve for the final velocity of the car just before it hits the truck. So replace the m with 1000, which is the mass of the car. Velocity, the initial velocity, 35 meters per second. Of course, the mass is still 1000. The final velocity before it hits the car, we don't know. So we call it v squared. The distance traveled, we don't know. We know it's 30 meters. It's fixed. Between the car and the truck is 30 meters. And the kinetic friction is 8,000 meters. So we try to solve for the value of v from this equation. So bring the numbers to one side. This term involving the v square, you just leave it on the left hand side. So using the calculator, you just evaluate this kinetic, initial kinetic energy minus the work done. That will be how much kinetic energy you have left before the car hits the truck. So the difference between these two is how much kinetic energy you have left. So from this amount of energy, you can find the value of V. So you have to take square root because there's a V square there. So square root of 745 is 27.3 meter per second. So that means this is the velocity. The velocity before, the velocity of the car before it hits the truck is 27.3 meter per second. Okay, any question?
No question, sir.
No.
All green.
No, then you read this question 5.3.
Qualitatively, how would the answer for the final velocity change in part B if raining during the incident explained?
Okay. Qualitatively, that means you don't have to calculate. You don't have to know the exact relationship like this in the first question here. Now, when it is raining, the frictional force will reduce. So the amount of kinetic energy that is used to overcome the friction is less. So you have a lot of kinetic energy left. So this a lot of kinetic energy left when you translate them into velocity. That means there's still a very high velocity. The speed is still very high. Okay, so to explain it properly, so if it rains, the friction will decrease. The F, the kinetic friction will decrease. So when the friction is reduced, the work done against friction is less. So you use up less kinetic energy. When you use up less kinetic energy, that means more kinetic energy is left within the car. More kinetic energy is left with the car. So the car, when it knock against another car, it will knock against the car with a higher velocity. So the velocity on impact is bigger. Or a very simple argument. Okay. Any question?